Hello everyone and welcome to today's lecture. Today we're going to be talking about arc length and surface area, which are two geometric quantities that we can measure using the single integral. So to start off, we'll start off talking about arc length and then see how to actually get a formula for surface area of what are called surfaces of revolution as we kind of progress through the lecture. But the first topic we're going to talk about is arc length. And specifically, this is for the arc length of a general function of x. If we're given a function of x, or y equals a function of x. So we have an x-axis, a y-axis, and suppose that we have some curve right here, some y equals f of x. And for this curve, we want to derive the actual physical length along the curve, which we call the arc length, from a point A to a point B along the x-axis. So the idea, just like many of the other ideas in this course, is to be able to figure out a formula for this arc length using the concept of Riemann sums. And it turns out that there's a very nice formula that we're going to derive that will directly give us the integral for the arc length of this curve. So specifically, the arc length is the actual physical length, if you were to say traverse this curve directly as you kind of move along the curve. If you take a ruler and make very, very small, say, measurements along this curve at each given, or a whole bunch of different small segments, you end up with the arc length. And this is exactly the procedure that we use when we want to get the formula for arc length, or derive the arc length formula. Because the idea here is, just like many of the other applications, is to partition our interval into a whole bunch of small subintervals. And I'm drawing here a small partitioning of this interval into a whole bunch of small pieces. And the idea now is that if we partition the curve into all of these small pieces, remember that we can do this with even finer and finer and finer partitions, so we can get very, very, very small and very, very, very precise. But the idea is that if we then add up the straight line segments, and I'll draw those in blue, from each individual points in this partition, we obtain a close approximation to the actual physical length of the curve. It's not exact, it's not an exact result, but in the limit, as this partition gets smaller and smaller and smaller, we expect that this value will converge to the exact length of the curve. This is exactly what happens. So this is what we call the arc length. So to develop a formula here, we want to label each one of the terms in our partition. We call this x1, x2, and so on and so forth. X3, and in general, the partition will go up to xn, because we might have n points in our partition. We call this the first point in our partition. We'll call it x0. So really, the partition is made up of all of these different subsegments, just like we did our Riemann sums, and the idea is that the width of each individual subsegment we can call delta xk. So if I sort of we'll just take one of these rectangle as an example and kind of blow it up into a bigger piece. You have here a rectangle width of delta xk. The top of the rectangle the top of the rectangle goes kind of like this. It goes from the function value here to the function value here. So you have a change of delta yk. That's not the height of the rectangle, but it's the height of this term right here, or this distance right here. That's delta yk. And because this is a right triangle, for every single one of these partitions, you have that delta sk squared is equal to delta xk squared plus delta yk squared. Or delta sk, which approximates the arc length on that interval, is equal to the square root of delta xk squared plus delta yk squared. And what this means is that the total arc length from A to B is approximated by the summation of all of these smaller arc lengths, or all of the approximations on each subinterval of the partition. So it's the sum from k equals 1 to n of delta sk, or the sum from k equals 1 to n of the square root of delta xk squared plus delta yk squared. The square root. So before we can take a limit, we need to do a little bit of restructuring of this, because it's not immediately in the form that we want it to take a Riemann sum limit. But doing that isn't too bad. We just have to actually end up using the mean value theorem. So what we have then is that what I'll call this summation right here Sn, because it turns out that this is going to be a Riemann sum that we end up taking the limit of as n goes to infinity, or the number of rectangles in our partition goes to infinity. So the first thing that I can do is factor out the delta xk squared under the square root. That's delta xk squared times 1 plus delta yk over delta xk squared. I make the square root a little bit longer so you can kind of fit the entire expression in right here. And so Sn, our expression for the Riemann sum, is the summation from k equals 1 to n. The square root of delta xk squared is just delta xk. So it's the square root of 1 plus delta yk over delta xk squared times delta xk. So our first simplification is really just an algebra simplification. We just kind of rewrite our summation term in a little bit nicer, a little bit more nice of a manner. The second main summation, or the second main simplification that we have to apply is the mean value theorem, because we want to find a better expression for this delta yk over delta xk. And it turns out, if you recall from the mean value theorem for derivatives from calculus 1, we have exactly that. We have that for any interval, in this case for the interval from xk minus 1 to the interval xk, the function value here maybe is going from this down to this right here, or the straight line segment is going from the value of the function at xk minus 1 to the value of the function at xk. There will always be a point in this interval where the derivative of the function at that point, in this case, say the point is right here at ck, say, there will always be a point ck where the derivative of the function f prime at ck is in fact equal to the average slope, the slope of this line. The slope of this line being delta yk over delta xk. So this is guaranteed for us by the mean value theorem. And what that means is that in this Riemann sum, in our Riemann sum, for every single subinterval, there's this point ck where this is true. So delta yk over delta xk can always be expressed as the value of the derivative of our function at some ck in the interval. So it's going to be 1 plus f prime at that value ck for the kth subinterval squared times delta xk. And now we are in the form to take the limit of this Riemann sum, because this is in fact a Riemann sum. It's a Riemann sum using the sample point ck, where ck is that point that's guaranteed from the mean value theorem. So we can consider the limit of Sn as n goes to infinity, and sure enough, the actual arc length then, which we'll call S, we could also call it SAB to be very specific, that this is the arc length from A to B. This is equal to the limit as n goes to infinity, as the partition gets smaller and smaller and smaller, of this Riemann sum right here that we were talking about earlier. And what this becomes for an actual integral formula is that this becomes the definite integral from a to b of the square root of 1 plus f prime of x squared, where f prime of x is the derivative of the function f squared dx. And so this is the simplified formula, or the most simple formula, expressing the arc length S in relation to the definite integral of a function on the interval from a to b. And I'll make this a little bit nicer. This should be f prime right here. A little bit nicer. But it turns out that this gives us a procedure now that we can use to evaluate the arc length along any function of x, no matter how complicated it is. If we can somehow evaluate this definite integral using the fundamental theorem of calculus or any of the many integration techniques that we've gone over, this gives us a procedure for solving for the arc length, the actual physical length of along that function curve. So let's see this in an example. We'll do one or two examples to kind of make sure that we're all set with using this formula. The first example that I'm going to go over is finding the arc length of the function y is equal to 1/2 x squared minus 1/4 the natural log of x from x equals 1 to x equals 2, or for x between 1 and 2. So if you're curious as to what this looks like, I'll bring up a plot right now. So this is a picture right here that I plotted using Desmos of this exact function right here. This is the x-axis. This is the y-axis. And this is the general function, 1/2 x squared minus 1/4 ln of x. But we're really only interested in this example from the arc length from 1 to 2. So I've colored that section of the function in red. So we want the actual physical length of this curve right here. The first thing that we need to do to use this formula is realize that, well, in the formula that we just derived, we have the derivative of the function. So we're going to want to use and take the derivative of this function. This is our f of x right here. So the first thing that we need to do is take the derivative of this function to use this formula. So f prime of x, this is going to be equal to the derivative of 1/2 x squared, which is just x. This will be minus the derivative of 1/4 or negative 1/4 ln of x, which is going to be 1/4 times 1 over x, or 1 over 4x. So this is the derivative that we're going to have to use in our arc length formula. So the formula for arc length that we derived gives us that what we're looking for, or the arc length s, is the definite integral. In this case, this is from x equals 1 to x equals 2 of the square root of 1 plus f prime of x squared dx, which is going to be the integral from 1 to 2 of the square root of 1 plus x minus 1 over 4x squared. And this integral, if we can go through and evaluate the integral, gives us exactly what we want, which is the value of this integral is going to be the exact value of the arc length along this curve. So at first this integral looks a little bit difficult, but sure enough we can simplify it by doing a little bit of algebra. This is going to be 1 plus x squared minus, it'll be 2 times x times 1 over 4x, which is going to be minus 1/2. I'm really just foiling out this square that we have here, so you got to foil it out. And then lastly you have plus 1 over 4 squared, which is 16 x squared. I'll make this a little bit, square it a little bit bigger so we can see this a little bit better. So 1 minus 1/2 is 1/2. And this integral just becomes the integral from 1 to 2 of the square root of 1/2 plus x squared plus 1 over 16 x squared dx. And this looks a little bit simpler than what we started with before, but it's a lot simpler if you remember that this polynomial right here factors actually very nicely. If you think about it for a little bit and try and factor this polynomial, sure enough, the polynomial that's under the square root is the exact same thing as x plus 1 over 4x squared. And if you don't believe me, you can FOIL that out. So FOIL this x plus 1 over 4x squared out, and this is exactly what you'll get. So this simplifies then. The square root of x plus 1 over 4x squared is the same thing as the absolute value of x plus 1 over 4x, but because x is positive on this interval, this is just equal to x plus 1 over 4x. Right, because this function is never negative on this interval from 1 to 2. And so this gives us that the arc length S is this integral right here, which we can evaluate using our standard method, which is to take the antiderivative of this function, which is x squared over 2. And then the antiderivative of this function is going to be 1/4 times the natural log of the absolute value of x from 2 to 1. And when you plug in 2 and you plug in 1 and you subtract the two values, you end up getting that this simplifies finally to 3/2 plus 1/4 natural log of 2, which is the exact value of the arc length of that segment that we talked about. And by the way, if you approximate this, this is approximately equal to, it's an irrational number, but it's approximately equal to 1.6732. Right, so the distance, let's say if you're measuring in meters, the arc length of this red section right here, if you were to measure exactly the exact value of this distance, is 3/2 plus 1/4 ln of 2, which is approximately equal to 1.6732 meters. So this is a pretty cool procedure, and you can see that the integral that you get for the arc length calculation could potentially be a very complicated integral. So it's gonna, in general, rely on all of our skills from before, which is, the fundamental theorem of calculus, U substitution, integration by parts, trigonometric substitution, partial fraction decomposition, right? All of the methods that we've talked about in terms of evaluating integrals. In order to get a given integral, you're going to have to kind of rely on those methods very, very heavily, because the integrals don't always end up being nice, but it's very powerful in the sense that this gives us a procedure to evaluate the actual physical length along any shape, no matter how complicated that shape is. So for the next example, what I want to show is how to go through and show a very, very nice geometric formula for the arc length of a circle. And if you've taken a pre-calculus course, you'll probably be familiar with the result that we're going to end up deriving. But let's say we have a circle of radius r. What we want to figure out is the arc length along a circle of radius r. Let's say we have our circle here, circle of radius r, and we want to go along the circle up to some angle theta, and we want to figure out the arc length, color it in red right here, from 0 angle up along to this point right here. So the physical value of length along the circle from here to here, or from theta equals 0 to theta equals some value. So the first thing to notice is that this is, say, x1 right here at this point, and this point right here is x2, and we want to figure out exactly what the arc length s is from x1 to x2. And just like before, the integral from x1 to x2 is going to be the integral of 1 plus f prime of x squared dx, where f is the y function, or the y coordinate on the circle for this part of the circle. So in order to figure out what f of x is, we need to take the circle equation and solve for y in the circle equation. Right, specifically, this is done by looking at here. Remember, this is the x-axis, and this is the y-axis. Remember, the equation of a circle of radius r is x squared plus y squared is equal to r squared. So that means that y squared is equal to r squared minus x squared. And so y is equal to plus or minus the square root of r squared minus x squared on the circle for all points x and y in the circle. Now we're only interested in the top half of the circle, so that's the positive part of this solution right here. And this is our f of x for this problem. So we don't have f of x in the formula, we have f prime of x. So what we need to do is take the derivative of this function with respect to x, and that's going to require the chain rule, because remember, f of x here is equal to r squared minus x squared to the 1/2. So using the chain rule, this is going to be 1/2 times r squared minus x squared to the negative 1/2 times negative 2x, or negative x over the square root of r squared minus x squared. So this is our f prime of x, and therefore this is what we have to plug in to use this formula right here. S is the integral from x1 to x2 of the square root of 1 plus, and then this squared is going to be x squared over r squared minus x squared dx. I'll move all this stuff over to the left a little bit so we have a little bit more room. I'll also put a line right here so you can kind of see this a little bit nicer. So if I bring this to common denominator by expressing 1 as r squared minus x squared over r squared minus x squared, this integral is just the integral from x1 to x2 of the square root of r squared minus x squared plus x squared over r squared minus x squared. The x squared terms cancel out. So this right here cancels with this right here. And we are left with the equation that s is equal to the integral from x1 to x2 of the square root of r squared over r squared minus x squared which we can use a little bit of algebra to simplify. Specifically, if we do that, and we factor out an r squared from the top and the bottom, we have that s is equal to the integral from x1 to x2 of the square root of r squared over r squared times 1 over 1 minus x over r squared. Dx. So I got this expression by noticing there's an r squared in the numerator, and if I factor out an r squared from both terms in the denominator, I get another r squared. So these two terms simplify very nicely for me. And the integral that we end up having to evaluate then is the integral from x1 to x2 of 1 over the square root of 1 minus x over r squared. And by using a u substitution and combined with the trig substitution, we can go through and get this integral. If you want to, you can first do a u substitution to get rid of this x over r. So you do u equals x over r. But you can just do a straight trig substitution if you want. That's perfectly fine as well. And that's what I'm going to do down here. So if we do x over r, the substitution, or the trig substitution, x over r is equal to cosine of theta then when I look for dx with respect to theta, we end up getting that dx over r is equal to negative sine theta d theta, or dx is equal to negative r sine theta d theta. So when we make this substitution, we end up getting that s is equal to the integral, and we have to think about our bounds here, how the bounds change with this substitution. But the integral of 1 over the square root of 1 minus cosine squared theta, when I plug in for x over r, dx is negative r sine theta d theta, and then the theta bounds, the new theta bounds here, remember x1 is at theta and x2 is at theta equals 0. So x1 is at theta and x2 is when theta equals 0. So this is an important step, always with trig substitution, remember, to be able to do this, to get the correct result. Well, this negative sign here switches the order of integration, and you should realize here now that the formula that we have for s, this integral, is then going to be r, because it's constant with respect to theta, times the integral from 0 to theta of sine of theta over, and 1 minus cosine squared theta is just sine squared theta. So this is the square root of sine squared of theta. And this is the absolute value of sine, but in the first quadrant, where we are here, the sign is positive. Really, in the first not just the first quadrant, but the entire first half. So for theta from 0 to pi, the sine function is positive. And because of that, this is the same thing as sine of theta over sine of theta, which is just 1. Square root of sine squared is just sine theta for theta from 0 to pi. So this becomes r times the integral from 0 to theta of 1 d theta, which is just equal to theta. So it's theta times r. This is what the arc length is. So this is an exact proof of why the arc length is s, or the arc length s for a circle is theta times r. And this is hopefully familiar to you, a familiar result to you from, say, a pre-calculus class, where you can use just straight geometry to derive this result. Specifically, if you notice that, right, any segment of a circle has to be similar to the circle itself, you'll notice very clearly that the arc length of a segment, which is s we're calling, right, s divided by the circumference of the circle has to be equal to the angle of that segment, theta, divided by 2 pi, where 2 pi is the total number of angles in this circle, or 360. So if s over the circumference of a circle is 2 pi times r, is equal to theta over 2 pi. If you solve this equation for s, the 2 pi's cancel out, and you're left with s is equal to theta times r. Alright, so this argument is a much more simpler argument using just geometry, straight geometry. But it's important that you understand how to use the arc length formula that we derived, because this is the more exact mathematical proof of why the arc length of a circle is theta times r. And the geometry argument only works for circles, while our formula that we derived for arc length works for any curve, no matter how complicated the curve is. as long as you have a derivative function such that this function 1 plus f prime squared, square root, is integrable. You can take the integral of the function. So this is a very, very important, a very, very important example showing how to use the formula.